Esperamos unos minutos más. Me indica que ya está siendo, se está llevando a cabo la transmisión en vivo en YouTube, aunque en YouTube no percibo que esté transmitiéndose. No sé si, Sandra, tú puedes checar eso, por favor.
Claro, dame oportunidad de revisar.
Unos minutos más. Me indica que ya está siendo Bien, ya lo veo en YouTube, ya está siendo transmitido. Damos unos minutos más a que se conecten más colegas de Soma. Un par de minutos más y luego damos inicio.
Ok, sí, está un poquito retrasada la transmisión, pero está.
Bien, ya lo veo en YouTube, ya está siendo transmitido. Damos unos minutos más a que se conecten más colegas de Soma. Un par de minutos más y luego damos inicio.
Ok, está un poquito retrasada la transmisión, pero está.
So Miguel, how much should I speak? Do I have 45 minutes, 1 hour? What? Should I pay attention to this or it's free?
Yeah, it's somewhat free, Nadia, but if it is of order 45 minutes or 50 minutes, it's better. So
Okay.
we can have some time for questions.
Okay, perfect.
So Miguel, how much should I speak? Do I have 45 minutes, 1 hour? What should I pay attention to it or?
Ok. Bueno, pues podemos empezar. Con el tiempo se irán agregando más colegas de la Sociedad Mexicana de Astrobiología. Antes que nada, quiero expresar el profundo deseo de la mesa directiva de la Sociedad Mexicana de Astrobiología de que ustedes y sus familias estén bien. Todos ustedes quienes nos acompañan como miembros de SOMA. A Nadia, por supuesto, que es nuestra ponente del día de hoy. Y a quienes nos acompañan a través del canal de YouTube de la sociedad. Espero que se encuentren todos muy bien ustedes y sus familias. Y les damos la más cordial bienvenida a todos los miembros de la sociedad que nos acompañan a través de esta liga Zoom y al público en general de YouTube. Es una cordial bienvenida. Les agradecemos mucho que estén aquí presentes para escuchar a la doctora Nadia Balucani en esta tercera conferencia del ciclo de astrobiología para todos que organizamos en la Sociedad Mexicana de Astrobiología. Bienvenida a Nadia, benvenuta Nadia, grazie mille, y cedo el micrófono a la doctora Sandra Ramírez, quien dará una reseña curricular de la profesora Nadia Balucani.
Gracias, Miguel. Buenos días a todos. Bienvenida, Nadia, nuevamente. Y gracias por tu participación. Bueno, simplemente comentarles algunos aspectos muy particulares y muy concretos del amplio currículum de nuestra ponente el día de hoy. Ella es una reconocida profesional de la astrobiología, tanto en Italia, su país de origen, como a nivel internacional. Entonces, la profesora Nadia Balucani se desempeña como profesora de tiempo completo en química en la Universidad de Perugia, en Italia. Es profesora y asesora de estudiantes tanto de licenciatura como de maestría en química, así como miembro de la Escuela de Doctorado de Ciencias Químicas de la propia Universidad de Perugia. Es una científica afiliada al Instituto de Planetología y de Astrofísica en Grenoble, en la Universidad de Grenoble en los Alpes. y también es un miembro asociado del Observatorio de Arcetri en el Instituto Nacional de Astrofísica en Italia. La profesora Nadia Balucani se graduó con una licenciatura en química con mención honorífica por la Universidad de Perugia. Realizó su doctorado en física química por la misma universidad, recibiendo el título en 1993, y posteriormente realizó un postdoctorado con el profesor Saikali en la Universidad de California en Berkeley. Fue miembro en el Comité Científico de la Sociedad Italiana de Astrobiología de 2012 a 2017 y miembro de la Agencia Espacial Italiana, la ASI, en el grupo de expertos en astrobiología de 2015 a 2018. Actualmente es miembro del Comité Ejecutivo de la Sociedad Italiana de Astrobiología desde 2018. Es autora o coautora en más de 200 publicaciones, con un alto porcentaje de ellas en revistas indizadas y de alto impacto. Y es miembro de algunas otras asociaciones internacionales como el Solís, como Faust. También participa en el programa del Proyecto Nacional de Italia de Astrobiología y es una excelente expositora. Yo he tenido la oportunidad de escucharla y vamos a tener una charla muy interesante y muy dinámica con ella. Entonces, bienvenida Nadia, te cedo la palabra. Now you are able to speak. Nadia, welcome again and thanks for your wishing in participating with us.
Muchas gracias. Lo siento que no puedo hablar español, so I will move to English, sorry. So I would like to thank you for the invitation that I appreciate very much. I'm always happy to share my work and my research with the general public or colleagues in our fields of expertise. As you said, I am a chemist, I'm a physical chemist, and indeed my field of expertise is gas phase chemistry. So maybe some of you were kind of puzzled by the title of this talk, because normally when you think of prebiotic chemistry, you have in mind maybe some biochemistry in solution, this kind of thing. So maybe it is a kind of contrast to see in the same and one after the other actually the words gas phase and prebiotic chemistry. But I hope I will convince you that this is actually not a strange thing. It is actually kind of important, and as we are going to see, important for us to understand how maybe the life started, at least in our planet. We know that it happened at least one time, no, once at home. So there must be a way for matter to move from the abiotic conditions to biology somehow. Okay, let me just spend a few words about my hometown. You probably know Italy very well. You certainly have heard about many beautiful towns in Italy: Rome, Venice, Florence, Naples, and so on. Perugia is not so famous, but believe me, it's at least as beautiful as these other towns that I mentioned. You can see a picture. It's a medieval town. This is the main square of my hometown of Perugia. You see where Perugia is located in Italy. It is called the Earth of Italy because it is exactly where the Earth is located normally, no, in a body. And at about 20 kilometers from Perugia, you can also see another famous and beautiful town, Assis, the town of St. Francis, that I'm sure that you know. My university is one actually of the oldest in Italy and all over the world. It was recognized actually in 1308 by the Pope. It was founded 50 years before. So it's a public-owned university with a long history, but believe me, we can also do science. This is how I hope I will convince you about that. This is a nice image. This is a Roman mosaic that is present in my department. I work at the Department of Chemistry, Biology, and Biotechnology of my university. But the question is that when you make a hole in Italy, you always find something. So when they were building our building, they found this Roman mosaic, which is now part of our own department. Not only history, our department is also recognized for the science it's producing, and in fact is one of the 13 excellence departments in chemistry in our country, in Italy, and it received special fundings for this. Okay, so I don't want to be too technical because I know that this is a presentation for general public. But let me just say that in my laboratory, we use both an experimental and theoretical approach. Here you can see our cross-beam machine. So as I said, I don't want to be too technical, but this machine allows us to investigate gas phase reaction isolated from the environment. This is very important, as we are going to see for the topic of today. So just remember this: we can investigate a gas phase reaction completely isolated from the surrounding environment. So this is important because we are able to reconstruct exactly what's going on at the atomic and molecular level. That's the right way to put it. So this technique is a kind of complex, and because you have to produce, as we're going to see, transient species in situ, locally, because otherwise those experiments are impossible. So this is a little bit limiting because it's not easy to produce these transient species, which are instead abundant in some extraterrestrial environment that we are going to mention in a while. So we need also to be back up in some cases, but in some other cases, actually, a theoretical approach, a computational approach is the only one which is possible. This is especially true when you are interested in reactions involving more than one transient species. In this case, to run an experiment is really difficult. So in my research group, we don't have only the experimental approach, but also a theoretical approach, which is helping us to investigate the reactions we are interested in, but which are not amenable to an experimental investigation. And unfortunately, there are plenty of them, as we are going to see. This is exactly the point. In some cases, a theoretical investigation is probably the only way to characterize some experiments because of the difficulty associated to the experimental work in these cases. The experimental technique we are using in my laboratory was developed more than 50 years ago now by people who were awarded the Nobel Prize because of its complexity and novelty back then. But in those days, this technique was essentially used to address fundamental aspects about reactivity. And only thanks to the improvement in technological improvements, now we can use this technique to address processes which are important in different fields of chemistry, like astrochemistry, which is in a way the mother, let's say, of astrobiology in a sense. In these experiments, as I said, we are, since the beginning, actually, since when this technique was developed, the main purpose is to understand which are the forces that control a reaction. So in this kind of experiments, we don't simply mix together the reactants. We prepare them in a very controlled manner. We make them to collide, and then we analyze the result of single reacting conditions. This because back then, when it was developed by those guys who got the Nobel Prize for it, it was important to understand the basic aspects of reactivity. But now the situation is that this approach nicely reproduces the very low density conditions of several extraterrestrial environments, which are of interest in prebiotic chemistry. And these are the environments we are going to speak today. The interstellar medium, actually several regions of the interstellar medium, and other rarefied environments, in particular, the atmospheres of planets, but the upper atmosphere of planets, because as we are going to see, the most interesting recent results on prebiotic chemistry in extraterrestrial environment are coming from these two different environments, the interstellar clouds and the upper atmosphere of planets. I insist on the word upper because we are not talking about the part of the planetary atmospheres where the gas is dense, but we are talking about the parts of the atmosphere where the gas is already rarefied, but we will see what I mean in a second. Okay, this is just to show you how this kind of approach works. As I said, we don't simply mix together the reactants, but we confine them in trains of particles that are made to collide in a very controlled manner. So for fundamental reason, this is important, as I said, to understand what's really going on when the old bonds are broken and the new bonds are formed. But in our case, there are other aspects which are more interesting because, as I said, we are going to simulate an environment where you do have only specific conditions and not all the conditions that you normally have in dense environments. Okay, so I mentioned several times extraterrestrial environments. So what do I mean with that? As I said, interstellar medium, planetary atmospheres, and also actually cometary come and tails, not comment and the tails. And the research we are running now in this context received funding from the European Union and also from the Italian Space Agency, exactly because by understanding these processes, we understand the chemical evolution actually of those environments up to prebiotic chemistry. That's the question. Okay, so let's try to focus on what I mean here with the prebiotic chemistry and what is the role of astrochemistry in prebiotic chemistry. Well, we are part of the universe, part of the galaxy, part of the universe. And it's very interesting to compare the average chemical composition of the human body that you see here in this table with the average chemical composition of the universe, because it's completely different. If we speak about mole fraction, by far the dominant element in the universe is hydrogen, followed by helium. As you see, practically there are just these two guys in the universe. I'm talking about baryonic matter, of course, and I'm not talking about dark matter in this context. And then the third most abundant element is oxygen, but it is present in a much smaller amount than carbon and nitrogen. Pay attention, oxygen, carbon, and nitrogen, these are the elements of life. Well, together with sulfur and also some phosphorus, actually. And then we have other elements, as you see, all of them are present in the trace amounts. But it's not only a problem of the elemental composition. Also, if you think of the kind of chemical species that you normally find in the galaxy and in the universe, you mainly have atomic species or very simple molecules, diatomic molecules, triatomic molecules, no more than that. Okay, so now if we compare the situation of the universe and the galaxy with that of a human body, we find a completely different situation. We still have plenty of hydrogen. Indeed, you know, that's a large part of our body is made up of water, so that's the hydrogen carried by water, essentially. We have plenty of oxygen, exactly for the same reason, and then carbon and nitrogen, because these elements belong to biochemical molecules. So not only we have a different elemental composition, but also the kind of molecules is completely different. So clearly, in going from whatever it was before the formation of our solar system up to us, there must have been a chemical differentiation. What do I mean with this word chemical differentiation? In different steps, the chemical composition of the matter must have changed up to the first cell or the first living entity. Maybe you think that if we compare ourselves to our home, the Earth, maybe the situation is getting better. It is not really so, because again, if we consider the elemental composition and mole fraction, we have plenty of oxygen, and then magnesium, silicon, iron, aluminum, they are part of the crust and the rest of the planet. And so, as you can see, we can say that we are chemically differentiated also from our own planet. Okay, so what do we know about the origin of life? Well, not much. There is a big problem here. The big problem is that we do not have a geological record, a solid geological record of what happened in the first part of the life of our planet. So we are forced to speculate. Okay, so these are the basic steps that are essentially accepted. There is kind of consensus about these basic steps that preceded the origin of life. So of course, we had the formation of the solar system and of the Earth 4.5 billion years ago. Then it took some time to have a stable hydrosphere, because of course the rock was melted to begin with. So, and of course water was essentially as vapor. So to have a stable hydrosphere, we had to wait a little bit for the crust to cool down. And then somehow it is believed that there must have been a moment where there was a massive organic synthesis. So this is a key word for me. Remember that, massive organic synthesis. I'll go back to that, to go to this in a while. And then somehow it is believed that there must have been first forms of life a little bit simpler than those we see now, based on RNA. There is not much consensus on this, but I'm not an expert of this topic, so I'm not insisting on that. And then the first DNA protein life, and finally the last unified common ancestor from which all of us, in a way, derived. So my contribution in this timeline of the original life is related to the very first steps of this sequence. So this is the focus of my presentation today. Well, let me be a little bit more precise. So there have been new evidence by analyzing several detrital zircons, which are not really rock, these are pieces of rock. So this is a little bit older than the oldest rock. And finally, it seems that the stable hydrosphere, maybe it was a little bit earlier than what we think. And inside one of these zircon, there is really something fantastic, a small blob of graphite, which appears to have the same carbon-13 carbon-12 ratio than life. So maybe all these steps have been even faster than what we thought. So there must have been mechanisms which are kind of efficient, because in a relatively short, because we are talking about anyhow millions of years. So in a relatively short time, somehow the first living organism appeared. So the key word for me here is the massive organic chemistry, as I said, because this is believed to be an important step. Why that? Why massive? Because the probability that life spontaneously emerged from organic compounds is very small. So you cannot rely on a small sample of organic compounds. So the idea is that there must have been a huge amount of organic compounds, and that somehow from this big soup, somehow you had the first replicating organism that then, in a way, used all the other organic compounds to feed itself. Well, this is kind of complex to think as a chemist. I am a chemist, many of you are astronomers, I think, but maybe you have you studied some organic chemistry in your life. The question is, how can you have a massive organic chemistry in a water-dominated environment? So we know that water is not a favorable solvent to have organic synthesis. So even now, if you think, even now after so many years of active biosynthesis and so on, if you compare the mass of organic compounds of all the living entities with the amount of water, you immediately realize that in a solvent which is not favorable for synthesis, also the chance that organic molecules could meet each other and, for instance, two amino acids and form a peptide bond, and this process is not favored at all by the presence of water. So it's really difficult to think that this massive organic synthesis could have occurred on the surface of the planet. That is essentially the point. The surface of the planet. Remember also that in the first stage of our planet formation, there was the Pangea Panthalassa. So most of the planet was actually covered by water. So it's really difficult to think of this massive organic synthesis stage in a context where you essentially don't have the favorable condition to have organic compounds form. That's the main point of this question. Indeed, this forced the scientists to think about an alternative explanation. So there are actually two possibilities, that two suggestions that have been put forward trying to explain this massive organic synthesis. And they go under the name endogenous synthesis and exogenous delivery. So I will tell you in a moment what I mean with these two terms. So the endogenous synthesis is the vision which was put forward by Stanley Miller after his famous experiment. So the idea is that with some source of energy, starting from molecules in the atmosphere, like methane and ammonia, so gaseous molecules, not in the oceans, but in the atmosphere, in the presence of some strong energy sources which are available back then, this could be the situation where, starting from this species and liquid water in the oceans, you finally are able to synthesize biological molecule with a biological potential, let's call it this way. This is not the only possible explanation. There is an alternative, which is called exogenous delivery. So the idea is that in the nebula which preceded the formation of our solar system, because our solar system was formed starting from a cold cloud, in these regions, we do see now in space that there are plenty of organic molecules. I will go back to this in a second. So the idea is that these molecules were already present when the solar system was formed. They didn't survive on Earth because Earth is too close to the sun. So when the sun was a young star, it ejected strong solar winds and UV photons. So all those molecules which were possibly present on our planet were destroyed. But then in a second moment, when finally the surface of the Earth cooled down and so on, different carriers, interplanetary dust particles, meteorites, asteroids, and comets brought those molecules down to the planet. So this is an alternative way to explain why so many organic molecules could have been present at that moment. So the idea is actually sustained by the observation the last years of many organic molecules in all the different stages in which you can describe the life cycle of stars and solar systems. So in diffuse clouds, then they become dense clouds under the appropriate conditions. Dense cloud can become an accretion disk. From the accretion disk, you have the formation of a stable solar system. And then when the central star dies, you have the spreading in space of all the elements synthesized by the nucleosynthesis of the star, and so on. So you are recirculating these atoms, but the important thing here is that in all these different stages, plenty of organic molecules, complex to some extent, have been observed. So this in a way sustain the suggestion that the prebiotic molecules from which probably life started are actually a legacy of the interstellar medium chemistry. That means the chemistry that occurred before the solar system was formed. But then these molecules had to be brought to the planet by the carriers because, as I said, those molecules, the original molecules possibly present on Earth, could not survive the initial stage, the ignition of the sun. Well, let me just spend a few words. I think that you are not, in general, you shouldn't be chemists, for what I understand. So what do I mean with the word prebiotic molecule? Well, there is not a strict definition. Let's put it this way. So I'm providing you my own definition. You are free to use it if you are interested, no problem. So prebiotic molecules are molecules which are simple enough to be formed in a totally abiotic processes. So there is no life, of course, but there is a but, of course, they must contain either the functional groups which are typical of biological molecules. For instance, if you think of an amino acid, you will have the aminic group and the carboxylic group. Or even if they don't hold these groups, they must be able to form them. So there must be precursors. But this is not enough, in my opinion, because not all these molecules then are able to evolve towards more complex species. So an important aspect, in my opinion, is that these molecules do have unsaturated bonds, multiple bonds, double bonds, triple bonds, because this becomes the preferential site for the chemical attack. One of these once these molecules are brought in a situation where the matter is dense and where the chemical evolution is easier. So the idea is, the hope in a way, is to find these kind of molecules that I put in the slide in space. Of course, the selection I made is not by chance. These molecules that you are seeing rotating in my slide have actually been observed in the interstellar clouds. So really, they might be the link between the chemistry, the completely different chemistry that I show you in space, and the chemistry of life, because they do have all the characteristics I mentioned. Either one of the functional groups typical of biological molecules, or anyway the capability of forming it and the capability to evolve towards much more complex species. Well, you are probably familiar with the basic concepts of related to the interstellar medium and interstellar clouds. You have roughly 1% of the interstellar clouds are formed by dust, all the rest is gaseous matter. As I said, the elemental composition is the elemental the abundances of the elements is completely different to what we are used to. This is the so-called periodic table of astronomers. Now we have the square of this, the square of the symbols are proportional to their abundance in space. As you can see, we practically have just hydrogen and helium, as I said, but we have carbon, nitrogen, and oxygen. So we have exactly the elements we need to build up prebiotic molecules. So which kind of a chemistry we expect? Simple, complex, or complex? And this chemistry does have an influence in the universe evolution and in the origin of life. Well, of course, when I say chemistry, I don't mean the chemistry of that you might think of, like an alchemist or magic potion. So certainly, this is not the chemistry taking place there. So why that's because the temperature is extremely low. Those clouds from which the solar systems are formed are around 10 Kelvin, 80 Kelvin, no more. So that means really low temperature. There is also low number density. So practically the matter is extremely rarefied. So these are not the favorable conditions for chemical transformations, because chemical reactions need molecular encounters and also energy to be promoted. So this is certainly not the scenario that you imagine as favorable for the chemical evolution. Why low temperature is a problem? Well, I have a cartoon to illustrate that. The idea is that in a reaction, normally you have to weaken or even break apart the old bonds in such a way that then the atoms rearrange themselves and form the new bond. Well, in this first part of the reaction, where you need to weaken or actually break apart the old bonds, and you need to provide energy to the system. Even when the reaction is very exothermic, when you have a huge release of energy, okay, that's unfortunately, that's the situation. Well, that means you need to activate, by providing energy, your reactants. So that's why low temperature environments are not favorable for chemical reaction. If we go to the low number density, that's even worse, because you have few molecular encounters. That means a little probability for chemical reaction to take place, because the reactants must meet each other. So consider that in space, you normally have so-called bimolecular collision. That means a collision with two bodies, but you don't have at all thermolecular collisions. Thermolecular collisions, I mean the collision among three molecules, are instead very common on Earth. In the air we are breathing now, you have thermolecular collision all over. In the condition of the interstellar clouds, the cold interstellar clouds, you have one thermolecular collision every billion years. So really, this cannot take place. Well, in spite of that, I mean, trying to understand if there is chemistry in these conditions, well, we will see that the answer is yes, because we do see molecules, also molecules kind of complex. And of course, we have to face the situation, I mean, the conditions of these spaces of this environment. So these reactions are going to be in the gas phase mostly. Not only that, because there are dust particles, as I said, but these reactions, those occurring in the gas phase, must be reactions that do not need an activation energy, because otherwise there is no way to promote the reaction. They must involve a transient species, either an ion or an open shell radical. This is why, as I said at the beginning, the technique I've been using my entire scientific life to work with, well, this technique is the perfect one, because we can isolate species and work with the transient species. There are, of course, also the presence of those dust grains which are covered by ice. This can also be a promoting site for chemistry. Well, as I said, yes, the answer is yes, there is chemistry, because You see, these are the molecules which have been identified so far in the interstellar medium and also circumstellar species. So you see that there are complex molecules, but not only that. Some of them have those prebiotic potential that was mentioned before. Not only that, there are almost 200 molecular species discovered so far. Less than 40 do not contain carbon. So we have plenty of organic molecules, complex to some extent. Not only that, but we see also a rich inventory of molecules in comets and especially in meteorites and asteroids. Really, the meteorites can be really rich of complex organic compounds. This is the case of the Murchison meteorites. As you can see, we actually have amino acids and amino acids inside inside this small body. Okay, so I spent some words in a way sustaining the so-called exogenous theory. I mean, I was mentioning why the scientific community believes that this this suggestion is feasible. But I have to say that in recent years, also the endogenous theory, which was a little bit abandoned in the last decades, well, now this view got new life in a way, because there is a special body in our solar system. It's not a planet, it's actually a moon. It's the large moon, actually, of Saturn, Titan. Well, this object is extremely interesting and is supporting a new vision of the endogenous synthesis. What's the situation with this interesting moon? Well, the main component of the atmosphere of Titan are molecular nitrogen and methane. These are roughly the percentage of the two. Well, the idea is that in the upper part of the atmosphere, so we are talking about the most rarefied part of the atmosphere of Titan, we are not talking about the atmosphere close to the surface. Well, in this situation, there are UV photons. Actually, we need vacuum UV photons or even extreme UV photons coming from the sun, a small percentage, but still there. And also energetic particles, again, cosmic rays, solar winds, but also the electrons from the magnetosphere of Saturn. They also play a game here. So these energetic photons and particles are able to activate methane and nitrogen, which are otherwise very stable molecules that do not react with each other. So we have the dissociation, photodissociation of methane and nitrogen, and even the ionization, because these are very energetic photons and particles. So after these processes, what we have is the formation of higher hydrocarbons and ionic species, but even nitrites. So nitrogen is also involved and it is included in compounds of this kind. Well, at a certain altitude, it has been observed an important amount of benzene, so not only aliphatic compounds, but also aromatic compounds, and then other complex organics. And actually, according to the Cassini measurements, to the ion mass spectrum on board Cassini, actually in this upper part of the atmosphere, where, as I said, the gas is kind of rarefied, yet you have the build-up of complex species. So many complex organics have been identified with a mass up to 350 Dalton, and actually it appears that there are huge macromolecules there. So these are, 8,000 Dalton. This is really the mass of a protein. Of course, there are no proteins, but these are macromolecules, possibly polymers, actually formed by these monomers. But the interesting thing of this, all this, is that these large molecules at the end will deposit on the Titan surface. The temperature of Titan is very low, it's 94 Kelvin. So these molecules, once they are able to deposit on Titan atmosphere, they don't do anything. But if you imagine that something similar ever happened in the primitive Earth, and this is a suggestion, well, those molecules, we know from lab experiments that these molecules, in the contact with the liquid water, can hydrolyze. So that means that actually they break up in simpler species, but then it comes the interesting part, because these smaller pieces in which these very large molecules can break up once they react with water. Among those species, we have amino acid and nucleobases, exactly the ingredients of life. This is extremely interesting because it's not actually the view suggested by Stanley Miller. It's a little bit different because you have first the complexity formed in the upper atmosphere of Titan, starting from very, very simple precursors, nitrogen and methane. And then these molecules, even larger than what you need, would be, I mean, that's the suggestion, would be broken apart. But in breaking apart, they become the biological molecules that you need. So the formation of the complex species actually starts in the upper part of the atmosphere in the gas phase, and only after that, these molecules, once reach the surface, not in the case of Titan because it's too cold, and there is water, but it's ice. But if these molecules are able to be in contact with the liquid water, then we know from lab experiments that the same kind of molecules undergo these reactions with water. That is not only the case of Titan, but also Pluto has a very similar situation. These are new findings by the New Horizon mission. So also in the case of Pluto, apparently there are the same macromolecules. They form this haze, similar to the case of Titan, and the particles of which the haze is formed are these macromolecules with plenty of nitrogen. So hydrogen, carbon, and nitrogen, organic macromolecules. Okay, so I hope I convinced you that either in the star-forming region or in planetary atmosphere, gas phase chemistry can be very important for our story about the origin of life because they form simple prebiotic molecules. These molecules can then accumulate, react, and possibly bring to the first biological molecules and the first form of life. This is a kind of summary of the molecules that we should search for. So molecules containing a CN bond, because that's one of the ingredients. These are molecules which are precursors of amino acid and nucleobases. Molecules holding a CO bonds, because these are also precursors of amino acid and sugars. And also molecules with many carbon atoms, because they provide already the skeleton for complex species. Okay, let me mention for completeness that there are other theories about the formation of these molecules that do not rely at all in gas phase processes. And I'm talking about the hydrothermal vents scenario, according to which these organic compounds were formed in the oceans without the need of gas phase chemistry. Okay, so now I would like to see with you how we understand this chemistry, because this is going to help us with this, putting the scenario and having the scenario, especially trying to answer. These processes occur only in our case, or potentially they occur elsewhere. So, to understand this chemistry preceding the formation of complex organic molecules, it is necessary a multidisciplinary approach. You cannot just simulate a planet in a flask. This is not the most detailed approach. So you have to interact. We chemists, we must interact with astronomers and planetary scientists, because of course they provide us with the information about the abundances of species that will become the reactants of our experiment. And then we need also modeling. So it's a complex discipline that goes from astrochemistry to astrobiology, in the sense that I mentioned. Here I mean the first step of astrobiology, the formation of prebiotic molecules. So in this, in the modelings, you have in the models you have both physical and chemical parameters. Of course, I'm more interested in the chemistry part. So in these models, you have hundreds of thousands of elementary reactions, including dissociation, excitation, ionization processes, and then the reaction involving the transient species, and of course heterogeneous processes. Well, in the models, for instance, in the model of interstellar chemistry, you might have something like 8,000 reactions. And this reaction, unfortunately, have not been characterized in lab experiments yet. Why that? Because as I mentioned in the introduction, these experiments are difficult. Are difficult because you have transient species that normally are not, they are not abundant at all on Earth, and it's difficult to produce in experiment. Personally, I mean, my contribution is related to the neutral molecular reaction, but of course there are many other groups working in IO molecule reaction, and of course also in heterogeneous and multiphases reaction. They, of course, all of them are providing important contribution to the chemical evolution of the universe. Well, I don't want to spend too much time in details, but let me just say that in these models, 10–20% of the reaction including have been studied. And so what are you doing when they have not been studied? Well, my colleagues doing modeling, they suggest possible parameters like the rate coefficient or the branching ratio, relying on similar cases. But unfortunately, this is not a safe approach, because there might be huge differences going from one reaction to another, even when they look very similar. So in principle, it is important to characterize each of these steps one by one. And how do we do that? Okay, there are essentially two experimental approaches that are important in this context. One is the one that I presented already at the beginning, the one I'm using in my laboratory. This approach is nicely simulating the very low number density environment, or if you prefer, the very low pressure, same thing, of the interstellar medium and of the upper planetary atmosphere. So we are working in a so-called collision-free, we are running collision-free experiments, in the sense that all the collisions of interest are the object of the study. But that's not enough, unfortunately, because not only the pressure is low, but also the temperature is low. In the interstellar clouds, you have the formation, the so-called star-forming region, the temperature must approach 10 Kelvin, so really cold. Not only that, also in the atmosphere, I mentioned Titan and Pluto. These are cold objects, so the temperature is extremely low, not as low as in the interstellar clouds, but it is extremely low also in those cases. We are talking about 100 Kelvin, for Pluto even less. In fact, nitrogen is forms also ice in the situation of Pluto. So the temperature is also very low. Unfortunately, there are no experimental techniques that are able to simulate both conditions. So there is a technique, the so-called CRESU, developed in REM, but now is available in many other experiments, that allow us to investigate gas phase reactions at the low temperature of interest. They were able to reach temperature as low as 6 Kelvin. So no problem about that. But they are not able to reproduce the very low number density. Experiments like the one we are using in my lab, well, in this case, we nicely reproduce the low pressure environment, but unfortunately, we cannot go temperature which are so low as the one reached in the CRESU experiment. So this is a little bit of a problem. Okay, this is a list of the systems that I investigated in my lab with my research group over several years. Some of them are of interest in the chemistry of interstellar clouds, some of them in the chemistry of Titan, and some others in the case of comets. And we are not the only research group working with this technique in this research topic, but there is also my colleague in Hawaii, Ralph Kaiser, that has done a huge amount of work on similar processes. Okay, in the two, as I said, none of the two techniques is able to give us all the information. So we need something that is able to do the job for us. So with my technique, we gain information on the several aspects. With the CRESU technique, the other aspect, both of them can be backed by theoretical calculations. The theoretical calculation actually can finally give us the answer, because once you have built an accurate potential energy surface representing the reaction you have in mind, then you can predict any parameter under whatever conditions. So the idea is that there is a strong synergy between experimental work and theoretical work, trying to obtain this important piece of information, which is the potential energy surface representing the reaction. Well, I'm used to show this picture because the idea is to be able to know everything about a reaction, and this is possible when you derive an accurate potential energy surface. So we are, I mean, the people doing the experiments are like the blind people, in the Indian legend that never met an elephant and had to answer to the question, what is an elephant? So for some of us, it's a rope, a tree, a snake. But then if we put all the information together, we finally might be able to obtain the elephant, the potential energy surface in our case. That means the perfect knowledge of that specific reaction. This has been done. This has been done for several reactions, unfortunately not very many. This is one of the case, the reaction between atomic fluorine and molecular hydrogen. This is a very important reaction in astrochemistry because it becomes a kind of signpost to determine the abundance of molecular hydrogen, which is difficult to detect. In this case, really, we have everything we need. For other cases, unfortunately, the situation is not so good. So I'm showing you some examples now, taken not only from my work, but also from the work of some colleagues. But I'm afraid I don't want to be too technical, so I will just give you some insight. From CRESO experiments, there have been huge surprise in the last 10 years or so, because people realize that when the temperature is so low, there are only other parts of the potential energy surface which are important. And these are the pre-reactive section. This came kind of unexpected. And why it's so important for the chemistry of the interstellar clouds? Because this makes some reaction which were not thought to be possible. This aspect make them possible, even at the low temperature of the interstellar medium. So there is this beautiful work by my colleague in UK, Dividend, where they were able to see an unexpected effect. And I'm speaking about this specific result to make you aware of how difficult and how important it is to characterize these reactions under the appropriate conditions, because this huge effect could not be observed by working at other temperatures. So they were able to see an alternative reaction mechanism, totally unexpected, but which promoted a lot the reaction. So that was really a huge achievement, confirmed by other experiments and also by some theoretical calculations. So really, it's not enough to investigate the reactions under conditions which are not the appropriate ones. So that's part of the message. Other aspects, by investigating these processes, unfortunately, sometimes we are kind of disappointed. Why that? Because, in our mind, we think that if you put together small pieces, you can build up complex species. Now, this is a kind of ordered way of thinking of our mind. Well, this is not always, it's not always so simple. So, for instance, in this reaction, it was expected that this molecule, which is a strong potential, prebiotic potential, could be formed because, we try to add pieces to complex molecule, hoping to have a more complex one. But it came kind of disappointing. Actually, this was not the case because the methyl isocyanide molecule was actually not formed because there is a competition. So without entering into the details of this complex potential energy surface, let's say that we were expecting the formation of this molecule with some complexity, and instead we have the breaking up of a carbon-carbon bond and the formation of another molecule which is not so complex. Well, actually, our experimental and theoretical work demonstrated that the complex species is formed in very small amount. This is because CC bonds are weaker. So once you hope you form complex species, then you might be disappointed because instead the carbon-carbon bond is the first one to break apart. At least we find a way to form this species, because there was no other way, no other explanation on how to form a cyanamide in the context of the interstellar clouds. But that was found in other cases. So for instance, pay attention to the first reaction. This is a reaction between two radicals, really difficult to study in lab experiments. So we know that this reaction produces this molecule. This molecule is called methanamine, and it's one of the prebiotic molecules that we saw in the animated slides in the beginning. So you hope that by using the same reactant, NH, and the ethyl radical rather than methyl, maybe you hope you might form this molecule, which is a little bit, which is more complex than the other one. This is actually this was a suggestion put forward by some colleagues in interstellar chemistry. This is a complex network that my colleagues have developed to explain the formation of ethanamine, which has been observed in the interstellar clouds. But then again, according to our work, what we saw that actually it is not the complex molecule to be formed mostly, but again, because of the weakness of carbon-carbon bonds, we have we don't reach the hoped degrees of complexity. So when you start this reaction, mostly you are going back to smaller pieces, and only a small fraction goes ahead with the complex species. Well, this is actually what expected in a sense, because we do see in space that the complex molecules are much, much rarer than simple molecules. So this is the reason. It's not enough that you put together more complex reactants, because unfortunately, these more complex reactants can can lead to products which are simpler than what you hoped, and destroying your conjecture. Okay, there are also successful examples, of course. Now I gave you just two very unpleasant cases. So for instance, we were able to explain how a molecule with a strong prebiotic potential, this molecule is glycolaldehyde. It's very important in the aldose sugar formation and so on. So glycolaldehyde is really a big player in prebiotic chemistry. So we found a way to produce it in the interstellar medium, starting from common precursors, which are ethanol, atomic chlorine and the OH radical, and atomic oxygen. So there are also positive examples. This reaction network, sorry if I'm jumping, worked very nicely, because it's able to reproduce the relative abundance of glycolaldehyde and ethanol under wide conditions, which are typical of the interstellar. So we are starting getting a lot of information on gas phase reactions, which are important in the stellar medium. And here I'm making a joke in a way, maybe we know too much because we know where they don't work. As I told you, the alternative is that the dust particles and the icy mantles are promoting these alternative ways of forming those molecules. This is a very interesting suggestion, because of course the presence of a surface will act as a catalyzer, will act as a third body to dissipate the surface energy and stabilize the molecules, exactly what it is missing, since three-body collisions are not possible in interstellar medium. And then it acts also as a concentrator. So according to many of my colleagues, the dust particles and their icy mantle can help a lot to produce prebiotic molecules. Those prebiotic molecules that then will be inherited in small bodies and brought to the newly formed planets. Well, there are problems also in this view, because the mobility of frozen species by low temperature is not well characterized. Then these molecules must go back to the gas phase, because we do see them in the gas phase. And so together with my colleagues in Barcelona and Torino, we have started several years ago to investigate at the atomic and molecular level also those processes, which up to then instead were investigated only in lab experiments, not reproducing the correct size of dust particles. And so we have learned many things. It's not so simple as it appeared, because in some cases you do not have the process you hope for, in this case as well. I mean, this is not only a problem of the gas phase. So for instance, the reaction between methyl radical and HCO, which should form acetaldehyde, actually has many competitors that in the presence of the ice molecules don't favor the formation of acetaldehyde as expected. And then we find even more interesting aspects, because the icy mantles of these particles are water molecules, and in some cases actually the radicals you are interested in are able to react directly with the water molecules, and that prevents the process you hope for. This is an example. For instance, the radical CN is able to react with the water molecules of the icy substrate. So it is not going as you hope, because you have competitive processes. Okay, just for the final part, let me take the Enterprise, fly from the interstellar medium to the system of Saturn, because I want to say a little bit about this fantastic moon of Saturn, Titan. Titan is a very large moon. It's larger than Mercury. And as I said, it has a very thick atmosphere, thicker than ours, actually. And the main component is molecular nitrogen, like here on Earth, actually even more, because it's more than 95%. Then we have a methane and other species, larger hydrocarbons and nitride. And then we have this haze, which is covering completely the planet. And this haze, as I said, is composed by macromolecules, organic macromolecules, very, very rich in nitrogen. And I commented already on this plot. So the idea is that we have this reactivity, this reaction starting from simple species in the upper atmosphere of Titan down to the formation of these molecules. Well, in my lab, we have investigated actually for a long time several processes involving atomic nitrogen in the electronically excited state. This is formed in an abundant way in the upper atmosphere of Titan. And it can react very nicely with the other molecules around there. And lately, we have extended this investigation to other molecules that are known to be present in the thermosphere of Titan, in the upper part. So what is the idea for all our experiments? That starting from this very simple species, you go to molecules with intermediate complexity. But something that we know from lab experiments is that these molecules have the capability of polymerizing very easily. So these molecules, once they are formed by those reactions, will react further and polymerize or copolymerize, forming the orange haze rich in carbon and nitrogen that we know is surrounding the moon. So you know that there has been this famous mission several years ago. Now the mission is over, the Cassini-Huygens mission, but now there is a renovated interest for this planet, because for this moon, sorry, because the ALMA telescope has been employed to assess several open questions that remain for this for the chemistry of the atmosphere of Titan. You can see here beautiful images concerning some molecules observed by ALMA in the atmosphere of Titan. Well, as I said at the beginning, you cannot simulate the atmosphere of a planet or a moon in a flask. So why that? Because there is a gradient of temperature, there is a gradient of pressure. So here as well, the winning approach is to use modeling, photochemical modeling. And in the last years, we were very fascinated by the possibility that in the conditions of Titan could be formed pyridine and pyrimidine, these are really prebiotic molecules. Why that? Because benzene is abundant in the upper atmosphere of Titan, and the atomic nitrogen in its first electronically excited state, which is formed there by several processes, is a very reactive species. So it was possible to think that actually it could lead to the formation of pyridine and pyrimidine. So we have tested this hypothesis in our laboratory. Why that? Because the ion neutral mass spectrometer on board Cassini identified several compounds, C5H5N, which has the mass of pyridine. I mean, they couldn't know because it was a mass spectrometer. They couldn't know if it was pyridine or not. And indeed, this molecule was searched by several researchers with ALMA because the transition are unknown and so on. As I said, these are really prebiotic molecules because 3 nucleobases have the so-called pyrimidine structure. That means that they have 2 nitrogen atoms in the aromatic ring this molecule as well. Okay, so we have investigated these reactions in our lab experiment. They were kind of disappointing because according to our experiments, that process doesn't work, those processes doesn't work because we actually have a ring contraction reaction. So again, we lose complexity by reaction and we don't increase complexity. Interesting the case of the reaction with toluene because we see that the presence of a methyl group somehow preserved a little bit the aromatic ring. We also went further by investigating the reaction of atomic nitrogen with pyridine, but we couldn't observe pyrimidine. So this sequence of steps, unfortunately, must be disregarded. It's pity because that means we are not going to publish on Science, but in another journal, because we couldn't prove that these species are formed. In the meantime, this group of people led by Connor Nixon, they were trying to observe pyridine and pyrimidine on Titan with ALMA. They insisted for many years, Connor told me, but all their attempts were unsuccessful. So this might be the reason for that, since there is enough atomic nitrogen in the upper atmosphere of Titan, even though you have benzene, even if doesn't work. Therefore, it doesn't work. The formation is not this one, but not only that. Actually, this species is going to destroy pyridine, leading to pyrrole. That means a smaller ring. Well, I'll give you some example. I don't want to, how to say, to stress you too much with all the details, but let me say that I hope I convince you that it's important to understand these processes in order to have a clear picture of what the possible processes that preceded the emergence of life, the chemical processes, not yet biochemical. It's important to know them, and a pivotal role is certainly played by gas phase chemistry. You can find these processes at work in interstellar clouds and also in the upper atmospheres of planets or moons once you have hydrocarbons. So the idea is that somehow we go from very simple species to more complex one and complex, and more complex and more complex. And this somehow has led to life. We know this happened at least in our planet. So we started with physics, we ended up with biology, and in between we have chemistry of increasing complexity. And it's important to understand each of these stages because these are going to control the conditions, the situation, the possibilities that this more complex chemistry emerges. This happened at home. Did it happen elsewhere? We don't know yet, but if we understand the basic chemical processes at the heart of this transformation, probably we can at least figure it out in a way. So these are certainly easy processes compared to the other steps that finally brought to life, but we know the aggregation of hydrogen, oxygen, nitrogen, carbon is occurring also now, and leading to molecules which have a strong prebiotic potential. This is happening in interstellar clouds that will form solar systems like our solar system, and this is happening also now in several bodies of our solar system like Titan. These are simple processes, as I said, compared to others which are called into play for the study of the origin of life. But if we understand how and when these processes occur, then we have some help to set the stage for the emergence of life to occur. So let me thank my co-workers and the funding agencies that allow me to work on this topic. And of course, I would like to thank you for your attention.
Well, thank you, Nadia, for this wonderful and very illustrative talk. Now we are going to take the questions, if it is okay for you.
Sure.
Por favor, recuerden, chicos y chicas asociados a SOMA, que pueden escribir sus preguntas en el chat, o igual pueden hacerlas abriendo su micrófono, pueden hacerlas directamente abriendo su micrófono. Bueno, tenemos un par de preguntas. We have a couple of questions here at Zoom. And Miguel is going to take care of the questions from YouTube. So Miguel, I will start with the Zoom and then we move to you. So Brian Pastor says, thank you for your talk. It was very informative. Last year, hemolythine, a large complex molecule similar to a protein, was found inside a meteorite. What type of conditions would it take to form this kind of molecule?
Well, the idea is that small bodies like meteorites, even larger ones like asteroids and so on, they are formed during the solar system formation. And some of them are formed in a region which is far enough from the sun, so that the original inventory of organic molecules formed in the star-forming region that finally became the solar system, they could be preserved inside or on more than on the surface, normally in some little caves that are present on the surface of these bodies. In those conditions, you might have also some water, and then you have processing because of solar photons or also cosmic rays and solar winds. So you might have a local processing in those small bodies that help those species to become more complex ones. This is the same story as for comets. You know that in comets, you might observe on the surface some not well characterized refractory materials, but we know it's based on organic chemistry. So something like kerogen or things like that. Why that? Because during the life of a comet, you have the processing of the molecules of the surface, and they become more and more complex. So indeed, we don't see this degree of complexity in the molecules of the interstellar medium, also because we see the molecules in the gas phase. But you imagine that in those dust particles that I mentioned, you have these molecules for a very long time, because we are talking about billion of years. And so these molecules join together and become more and more complex. So it's extremely interesting because in this, especially in a class of meteorites, those which are rich of carbon compounds, really you find very, very complex species, including amino acids, and all sorts of molecules. Certainly, this is a piece of evidence that sustains the possibility that these very complex molecules were actually brought to Earth as such. And during the entering in the atmosphere, you might think that those molecules are getting destroyed, which is probably true for those which are really on the surface, but we know that some of them are preserved because we do find them inside the meteorites. So certainly they can be the seeds of life coming from the sun, from the sky, which is a little bit amazing, because we, in a way, we might even think that the organic chemistry that preceded the life was actually extraterrestrial. So we are, in a way, the offspring, the springs of extraterrestrial chemistry in a way.
Okay, thank you. We have another question that probably is related with this last part that you were talking about. It is from Santiago Cadena. It says, thanks for the presentation, quite interesting. I've heard of detecting organic molecules in space, but is there really an organic molecule that is an irrefutable sign of life? So far, all the organic molecules that have been found have an abiotic origin.
Yes, definitely. So the idea is not that we do have life in interstellar clouds, also because it's extremely difficult to think of any form of life which could resist in those harsh conditions. The idea is not that life is developed there. The idea is that in the interstellar medium, you have regions where the chemical complexity can increase up to not biological molecule, not to life, but to these prebiotic species that when those species are brought to a favorable environment, they can evolve towards biological molecules. And once you have an accumulation of biological molecules, or what we call biological molecules, you might have somehow life starting. So the idea is not panspermia. It's not that you are having life in space and that this life comes to Earth or other planets. No, the idea is that the chemistry that precedes life can originate from these exotic environments. And why we are playing with this idea, because as I said at the beginning, it's not easy otherwise to explain why you have, why we think we had, I should say, this massive organic synthesis in a very unfavorable environment as the planet Earth was at the beginning. Keep in mind that, okay, certainly when I say unfavorable, I have in mind organic chemistry, and I have in mind organic chemistry on the surface of the planet. You might think it's a little bit funny to think, okay, but certainly the interstellar medium is less favorable, which is true in a way, but molecules there are formed in a very long time lapse, not like in the case of Earth. Another thing that I would like to say is that no real biological molecule has been observed so far. You know that there was some debate about the detection of the simplest amino acid, which is glycine. Glycine is actually simpler than many molecules that we saw in that table. And there was a tentative detection, which was disputed. So at the moment, in the interstellar medium, there is no consensus of the fact that glycine, the simplest amino acid, is present there. But I think this is not really the point, because the point is to have those molecules that once brought to Earth will evolve. You don't need to see glycine. It's enough to see a precursor of glycine, because that precursor, in contact with the liquid water of the ocean, of the terrestrial ocean, will become glycine. That's the point. Because you can imagine more steps in this chemical growth. Some steps occurring in space, and the final steps occurring here at home. So the idea why we are playing so much with these ideas, because if we are able to prove that this works, then since those molecules are really ubiquitous, most star-forming regions share the same inventory of molecules. So if we believe in this suggestion, then every time you will have a planet like the Earth in the right place with the right characteristics, with the chance to have liquid water on the surface, more than liquid water, I would say oceans, then the molecules carried by meteorites, asteroids, comets, even interplanetary dust particles, those molecules in contact with liquid water will evolve. So that's the importance in the context of astrobiology, no? Because most of us will have her own ideas about the fact that life is spread in the universe or not, or we are the exceptional case. Each of us has his own idea on that, and it's difficult to sustain one suggestion or the other. But certainly, if we find common mechanism, then you can have some insights, let's say.
Okay, thank you, Nadia. I have a question on myself, probably a broader question. Considering this idea of the massive organic synthesis and in a more general frame, thinking about the terrestrial planets in the solar system, it seems that it is, or it was quite easy to have these organic molecules widespread among the terrestrial planets. We know the history of them, the evolution, Mercury very close to the sun, so very high temperatures, very bad environment for chemistry. Also, something similar happened to Venus. But what about Mars? Could it be possible that some of these organic molecules could be preserved, I mean, in the geological time of the planet under the surface of Mars? And could it be a possibility to find them with these new missions that are precisely looking above the surface? What do you think?
This is a very interesting question, definitely. So what we know for sure is that the surface of Mars, I mean, is too much depleted of organic molecules. We should have found much more organic chemistry than what we did. Why we say that? Because you can make a simple calculation by considering all the interstellar dust particles that fall down and micrometeorites and so on. It is possible to estimate the amount of organic compounds that you should find on the surface of Mars. That we didn't. So it is obvious that on the surface of Mars there are some processes, some chemical processes that very efficiently degrade these molecules because we didn't find them. This is, of course, true for the surface, for the external crust, because there are several explanations. There is a very oxidizing environment. Well, again, I want to go too technical, but I mean, there is an explanation for what we are observing. But indeed, this is true only at the contact between the surface and the atmosphere of Mars. So yes, definitely, if there are organic compounds, they could have been preserved. I would say just 1 millimeter below the surface. I mean, you don't need to go very deep because those processes are active exactly at the boundary between the surface and the atmosphere. And indeed, the new mission as this this is one of the aims of the new mission, because they want to drill a little bit the surface, searching for organic compounds below the surface. I'm very curious to see what will happen, because yes, in principle, I expect to find them there, but we will see. If they don't, really, this is a mystery, because we expect to find some organics. I mean, some of them were even on the moon, so why they're not on Mars? I mean, that would be really amazing. So I'm really curious to see if they are able to find some organic molecules just below the surface.
Okay, and then they will be a challenge to determine if they can be justified, if I can say that, in from a very chemical point of view, or if they could be related to some biological activity.
Yes, well, you know, it's never so easy. You know that there was this famous case of methane release, no, in the atmosphere of Mars. The first time nobody believed it practically, but then it happened several times. So apparently there are small movement of the crust, and they cause a plume of methane to come out, and then methane is quickly oxidized to CO and CO2, no, in the atmosphere. But I mean, it was seen. So that means there must be an organic reservoir somehow, no, somewhere. Also, the presence of methane is bizarre, because we know that Mars is a very oxidizing environment in general. So to find the carbon species were really, I mean, the most reduced version of carbon as a chemist, I have to say it's really a little bit of a shock. So of course, the first thing which comes to your mind is the presence of methanogens, some bacteria that are able to produce methane. But there are other abiotic possibilities, explanation. Not so many. I have to say, not so many, because to form methane in those conditions, you need this process serpentinization. I don't know if you heard about it. And serpentinization needs liquid water. So it's a little bit bizarre. There could be other explanation. For instance, that methane was present as a form of ice in clathrates and since the beginning. But that means that really there is no exchange between the matter below the surface and the surface itself. But okay, I'm really curious, and hope that soon we will have some answer to this to this question.
Yes, sure. Everybody's expecting new information about this Mars mission. Well, Brian
Absolutely.
comes back and he says, proteins and amino acids doesn't have a large lifetime. So it's kind of difficult to me to understand how some prebiotic molecules can be preserved for these 1,000 years in the solar system. Does the low temperature and pressure would be a key to preserve these molecules?
Well, not really, because the problem there is the exposure to UV light and cosmic rays and solar winds. Most of organic molecules are very sensitive to light, UV light in particular, and of course this is a problem. But you have to think that saying that we have in mind the molecules which are on the surface of those bodies, because the molecules which are below the surface will be preserved. We do see it also in comets. If you think, comets are exposed to plenty of UV light and other particles, and in fact, you do see this refractory material on the surface of comets. Yet the comets continuously the gas from the inside, So you have to think this way. Everything which is exposed will be burned, let's say, by UV lights and other particles rich of energy. But what is below is preserved. So that's the idea.
Okay, thank you. Well, we don't have any more questions from the Zoom chat. Miguel, do you have any additional question from YouTube people?
No, I don't see questions in the YouTube chat. I hope I'm doing properly the transmission, although there is a comment there, so that means that the chat is working. So I invite the people following us in YouTube to make a question if they wish. And while they do that, I have many questions, Nadia, but they are more related to my ignorance. So I will place more curiosity. You mentioned when showing a picture of Titan's atmosphere that the UV photons are, of course, important for ionizing or dissociating methane. And here the curiosity is the UV ultraviolet field of the sun sufficiently strong for these processes? Because I'm thinking that the Titan is too distant.
Absolutely. So of course the photon flux at the relevant wavelength is small, because it's small in general, coming from the sun, of course, and then it's far away. So for instance, compared to the case of Earth, it will be much lower because of the distance. Anyway, there is a portion of these photons. And also, you know that the sun has a local peak at the Lyman alpha emission. And actually, methane dissociates at the Lyman alpha wavelength. And in fact, this is going to be a favorable process exactly because of that. The situation is actually worse for nitrogen, because nitrogen indeed, to dissociate nitrogen, you need photons with a wavelength shorter than 100 nanometers. Actually, I would say even 80 nanometers. And so it's a tiny amount of photons are coming from the sun in that spectral range. Luckily for us, because these are not nice photons. Yes, suggest, I mean, your comment is correct. Yet some photons arrive. So those which arrive are able to, how do we know that? Because we do see nitrogen included in organic molecules. So not only methane is growing up, forming other large hydrocarbons, but also nitrogen. There are also the particles, energetic particles, they also play a role. But for what I could see, according to the model, most of the job is done by solar photons. So it is, of course, solar winds and cosmic rays also contribute to break up these very stable molecules, and also the electrons coming from the magnetosphere of Saturn. But for what I could see during the daytime, I mean, when you have insolation, the solar photons are doing the work. Keep in mind that also you have plenty of time. So this is part of the story in a way. So we don't need to think of fast processes on our time scale. We are talking about the life of a time lapse, which is the life of the solar system, to build up those species. Anyway, in the case of Titan, for what I could read, according to the photochemical models, really the chemistry is very rich. I mean, it's more, that atmosphere is more active than ours. It is believed to be the most reactive atmospheres in the solar system, in spite of the distance from the sun. Maybe rather than in spite, maybe I should say even thanks, because when it comes to organic, when it comes to chemical complexity, it's kind of like the Goldilocks story. You need some energy because you need to break up the very stable molecules that accumulate in an atmosphere. That's true. But if you have too much energy, then you go back to the case of mercury, then all the molecules are destroyed. So you need some energy to promote chemistry, but not too much, because otherwise you break back the complex molecules. Complex molecules are much, much more fragile than simple molecules because of the weakness of the carbon-carbon bond, as I was mentioning before. So you need really a strange compromise, let's say, some energy to start the process, but not too much, because otherwise you destroy what you created before. And that's maybe one of the reasons why we do see so many molecules in cold clouds. The richest places in the interstellar medium of complex molecules is CMC-1, a cold cloud. So there you find the largest molecules in the list, the molecules with 13 carbon atoms, in the cold cloud, not in the warm and not in the very cold ones. Because complexity has to be reached, that's true, but then it has to be preserved. So if you have too much energy around, then you don't preserve it. That's my feeling as a chemist.
Yeah, thank you. I am checking here on the other screen. I don't see questions from our friends following us in YouTube. And I don't see more questions from members of the society. If you have more questions, this is the last chance. Otherwise, we move on. No more questions, as I see. So, Sandra, would you like to close?
Yes, thank you, Miguel. Well, thank you to everybody who was joining us today. Gracias a todos los colegas, estudiantes, profesores que nos acompañaron hoy. Nadia, thank you very much for your talk. It's a huge amount of work there. It represents, I mean, clearly we can see all the years that you have been following this topic. I found very fascinating this in deep role of chemistry about planetary sciences, astrophysics, and so on. I am also a chemist by formation, by basic formation. So I am fascinated, and a wonderful talk. And I mean, as I said at the beginning, also you are a very good speaker. So thank you very much for joining this activity for SOMA, and hope we can meet soon, both virtually and in person. So all the best for you, and thank you again. And thanks to everybody. Gracias a todos.
It has been a pleasure, a real pleasure.
Muy bien, gracias a todos de nuevo en este